by all possible products so that for A inverse Bn and B and
Okay. Maybe we can talk about that at the end of class. So, sorry, I'm just going to stand here on the side to see if the camera is going to follow me or not, and then we'll see how to proceed. But what I was discussing with you last time was the different definitions of an algebra, right? And so we had the first two definitions were more familiar and had to do with being a vector space and a ring. And then the third definition was a little bit stranger because it didn't explicitly mention that what you had in your hand should be a ring. It just had these properties involving the tensor product. And somehow the fact that you have a ring is encoded in those properties. I think this is not going to work, so maybe we'll stick to these boards again today. So the last thing that I was trying to argue was this, that if you have a ring, A is a ring, then you have a multiplication, right? You have this multiplication in the ring. And what I wanted to argue, and I didn't get to argue, is that this multiplication gives you a multiplication at the level of the tensor product. And so I kind of waved my hands as to why this was true. But so what I want to do today is give you a better understanding of why this is true. And so that's what we're going to do now. Okay. So what I want to do is give you kind of a review of tensor products and how to work with them. And that's my goal for today. My goal for today is a humble goal to just talk a little bit about tensor products and help you understand some of their properties and how to prove things about them. Okay. So we're going to call the class Fun with Tensor Products today. This goes with the idea that we're going to lose our fear of tensor products and learn to appreciate them. Okay. So here's an extremely important property of tensor products, universal property. The universal property of tensor products is the following. It consists of two things. First of all, the map this map is bilinear. Okay. So let's say V and W are vector spaces. Okay. So I have a map from here to here, which remember, the elements here are just pairs of a vector in V and a vector in W. And I can take this and map it into the tensor of V and W. Okay. And the first thing I want to claim is that this map is bilinear. Okay. Remember, a map is bilinear if when you fix, I mean, I wrote it down, let me say it a little bit differently today. If you fix v, you get a linear function of w. So this is linear in w for fixed v, and linear in v for any fixed w. So this map is bilinear. But the next thing I want to say is that this is the universal bilinear map. So what do I mean by that? I mean that if you have any other bilinear map from the product v of w to anywhere, from the direct product to any vector space, then there is a unique linear function from the tensor product to L such that this holds. And let's see in a picture what this means. Oh, sorry, this is a tilde. So let's see what this means in a picture. What this means is the following. Let's say that you have any bilinear map, from the direct product to any L. Okay? Yep.
What kind of thing is L?
L is a vector space. So maybe I'll write it up here. If you have any bilinear map from here to here, then we say that it factors through this one. And what that means is that we have this bilinear map, which is kind of a horizontal bilinear map in this picture. Right? And so what, yeah?
Sorry, I'll let you finish this.
Okay. So what I'm saying is that given any function that you want to put here, you can always think of it as our universal one, phi, which is bilinear, composed with some linear map here, f bar, s tilde. Okay? So that this commutes. Okay? Okay? So I'm saying any bilinear map from v times w to any L is kind of an evaluation of the universal one. Okay. That's what this property says. Yep.
So a couple of questions. I know it's a little stickler about notation. So is this order of the this being on the horizontal, being horizontal with respect to the direct product, this tensor product being there is the same? Is this the same as having it be below, or is this just a matter of convention, or?
So the question is basically why did I draw this in the way that I drew it, and it's just usual to draw it in this way. So it doesn't really matter that what is vertical, what is it doesn't matter. All that matters is that f is the composition of these two functions.
Okay, so all right.
I don't mean anything else by this picture.
You just making sure.
And you're probably confused because I call it the horizontal map, but there's nothing horizontal about it except that I drew it that way. Okay. Okay, so that's the universal property. And an extremely important property. Maybe I'll keep the definition of bilinear here. And so what we're going to do is first prove this property, and then use this property. Okay? So, proof. So first, why is this really a bilinear map? Well, that's exactly by the definition of the tensor product, right? I mean, we instituted that in the tensor product, V tensor W1 plus W2 should be V tensor W1 plus V tensor W2, etc. We instituted all these properties, and these properties exactly say that this is a bilinear function. Okay. So this is clear from the definitions. Now let's prove the second one. Let's say that I have a bilinear function f like this. Okay. So given f like this bilinear, define f bar, and I do mean f bar now. That's why I got a little bit confused a second ago. Okay. Now, remember that what I mean by this is that this is the free vector space generated by this set. Okay. And so I'm taking every single element of v times w and declaring it to be a basis vector, and making this huge vector space with that as a basis. And so given that this is a free vector space, all I have to do is decide what I do to each basis vector. Okay? And so what I'm going to do is that I'm going to send VW to, what should I send it to? Well, there's not that much I can do except plug in f. F of VW. Okay? And maybe just so that you don't get confused by the notation, this I'm regarding as a basis of this vector space, as a basis element of this vector space. Okay? And so let me actually call it E sub that so that it sounds like it's a basis element. Okay? So what I'm saying is that the free vector space generated by this is just the span of the basis vectors E sub VW, where V is in V and W is in W. Okay? And so I define this and I extend linearly to make a linear function. I define it on the basis and I extend linearly. Okay. So I have defined a function from the free vector space to L. Okay. Now what do I want to do? The reason that I do this is that, remember, that the way that I define the tensor product, I define the tensor product to be a quotient of this thing. I define it to be this modulo an ideal where this is generated by a bunch of things. Okay. So what were the things? We wrote it last time, right? So, but now let me write it in this notation with the e's, okay? Just so that maybe it's a little bit clearer. So E sub V plus V prime comma W minus E sub VW minus E sub V prime W.
So you're saying this is true for every basis vector, or any of your choice, right?
Right now I'm defining an ideal. I'm defining an ideal generated by this and by E sub lambda V comma W minus lambda E sub V comma W, etc. And so this basically says, I mean, I'm encoding into this that for fixed W, if I set this ideal equal to 0, then I'm going to get linearity in the first coordinate, both with respect to sum and with respect to scalar multiplication. Okay, and then I do the same thing for the other coordinate. Okay, so remember, I mean, I wrote this last time. You have the same property, but with V and W switched. Okay, and so here I have my function from this space to L, and now I want to make it descend to this mod I. And so to do that, all I have to check is that the function evaluated at I is equal to 0. Okay, so to make it descend to the quotient group, or I mean in this case it's just a quotient vector space, mod I to L, I just need to check that f bar of the ideal that I'm running out by is equal to 0. That I is in the kernel of the ideal. That's how you define functions on a quotient vector space. Yeah.
Does descent to, is this similar to restricting to? Because I feel like the tensor product doesn't live in the same thing as the direct product.
So the question is, what does descent to compare to restrict to? So remember, if you have a function from A to B, and then you want to kind of restrict it to a subring of A to B, that's called restriction. But when I say that a function descends, I mean that I want to take a function from A to B, and from that, get a function from A mod I to B. So that's called descending the function. And to do that, all I have to make sure is that, because basically I want to define f bar on cosets here. Right? And so to make sure that f bar takes, basically I want to make sure that to define f twiddle correctly, I need to make sure that f bar takes constant value on cosets of I. And to say that f bar takes constant value on cosets of I is to say that f bar of I is 0. Okay? And I'll ask you to just pause the video, rewind, and let me say it 5 times in a row, and then you'll get used to what I just said.
But you're not claiming that f tilde and f bar are the same.
I'm not claiming that these are the same because they have different codomains, but I'm saying that this one is inherited from this one as soon as I check this property. Okay? But this property actually is very easy to check because to check that this is equal to 0, I just need to check that f bar on the generators equals 0. And you'll see that actually that's, let's go ahead and check it for this, for example. F bar of E sub V plus V prime comma W minus E sub VW minus E sub V prime comma W. Well, what is this? F bar of E sub something is just evaluating F V plus V prime comma W minus F bar of this. And notice that I'm using the linearity of F bar. So I get this. And I need to argue why this is 0. And why is this 0? Because F is okay. You said linear then bilinear, and I also said linear then bilinear. You have to be very careful because linear and bilinear are different things. And F is not linear. We never claim that it's linear. But F is bilinear, meaning that if I keep W fixed, then it's linear in the first argument.
It is fixed here.
And here, for these 3 things, W is fixed. And so we have linearity in the first argument, and this is equal to 0. Okay? And so that checks that f bar sends this to 0, and by a very similar argument, f bar sends the other things to 0. Okay, so you'd have to check it for the other generators as well, but that's very straightforward, and that completes the proof. Okay. Any questions about that proof? Yeah.
Why do you have to check all the generators? If one of the generators is set to 0, then doesn't that mean it's going to be in this empty?
No, so the question is why I need to check all the generators here, and the answer is that if I want to check that f bar of the whole ideal is equal to 0, then what I do, I is a linear space, right? And so I check that f bar takes the generators to 0, and then by linearity is going to take all of I to 0. But I need to check that every single generator goes to 0. This is one of these proofs, and you'll encounter proofs like this more as you go on into your mathematical careers, where I don't know about you, but I feel like we didn't do anything. It's kind of like it's kind of a very formal computation, and you didn't really have any clever ideas, and you just kind of let everything kind of checks the way it's supposed to. And the reason for that actually is that you have the right thing you want to prove. So the effort here is not improving this. You just have to kind of look through the definitions, make sure that everything makes sense. But the merit is stating the right thing. And if you state the right thing, the proof is actually pretty easy, straightforward. This is very often true when you have these universal properties. So you'll see them more in your mathematical life. And so this is the universal property. This is how you prove it. And now we're going to use it. We're going to apply it. Yeah? No, so the question is whether there's a formula for I, and I mean this is the formula in the sense that, I mean the way that you specify an ideal generally is by, there's a couple of ways of specifying ideals. One is by giving generators, which is what I did, or another typical one is by showing that it's a kernel of a map, which I didn't do, but you could do. But yeah, I mean I would say this is an explicit formula for the ideal. Okay, so that's the proof. And now let's use it. Let's put this to use. Yeah?
Another question.
Uh-huh.
So would this be what we would use if we wanted to show, let's say, for example, an example, if I had would this be a tool to show that, for example, we had two non-zero bases, that, for example, a basis B and double, and I think there's tensor. Could use that to show that it is the other side is non-zero as well, or?
Yes. So the question was, is this the right tool to prove blah? And the answer generally to that question is yes. This is a very useful tool to prove a lot of things that you are trying to prove about tensor products, and I'm going to give you several examples, including the one that you mentioned, but there's other ones. Okay. The point is this. The point is that you have probably figured out that it's a little bit tricky to define functions from a tensor product to something. But this does it for you. Because this says, if you have a bilinear map, which it's easy to define, I mean, if you can come up with a bilinear map, then that is going to give you a map from the tensor product. And so this is a very useful way to construct maps from a tensor product to somewhere. That's what we're going to do. And let me give you a very simple example. You have, I mean, I erased it, but here, if A is a ring, so here's an easy example. A is a ring. You have the multiplication of A. So do you agree that multiplication is bilinear? Think about what that means. It means that if you fix, so phi of VW is V times W in a ring. So if you fix V is multiplication linear in W. In other words, it's V times W plus W prime equals V times W plus V times W prime. That's true, and that's the distributive law. And you can check that multiplication is a bilinear map. That's, I mean, it's clear from the definitions. This is bilinear. Therefore, the universal property says that, let me maybe draw the picture so that we get used to it. Here's our multiplication. And the universal property says that this has to factor through phi. In other words, here's phi. Here's the tensor product. And I must have a map here guaranteed by the universal property. And that map is exactly the multiplication that I'm trying to define. And so that is the conceptual reason why I can do this, and everything works out. And this is going to show why algebras in the sense of 2, of definition 2, are the same thing as algebras in the sense of definition 3. This was kind of our missing step. And it's an immediate consequence of the fact that multiplication is a bilinear map. Okay. So that's going to be our example. I'll call it example 0 to be consistent with the numbering that I have in my notebook. Let me now talk about example 1, which is something that I also mentioned last time and I want to make more explicit today. If A is a K-algebra, then when I take that K-algebra and I tensor it with my field, let me go down here. When I tensor it with my field, I get an isomorphic K-algebra. I mentioned this last time, so let's prove it now. And I gave you an idea of how to prove it, but let's try to prove it from this point of view. Okay. We have an isomorphism that we want to show, and so we need maps. We need one map and prove that that map is actually an isomorphism. Okay. And now we have a tool for producing maps from a bilinear, from a tensor product to something. So let's produce this map from here to here. So to produce a map from, let's see, I called it F twiddle from here to here. Okay, I'm suggestively calling it F twiddle already. I just need to make it descend from somewhere. I need to make it descend from this, from some bilinear map. Okay? So where am I going to find a bilinear map? Well, I need to build it. So let's see if we can find an obvious map here. Let's take something here. Okay, so something here is going to be a constant in my field and an element of my algebra. What should I send that to? Lambda A. I mean, it seems like it. Now, what does lambda A mean? A is an algebra, and therefore, in particular, it's a vector space. And since it's a vector space, I can multiply by a scalar. And that's what I mean here. Okay? Is this bilinear? For example, if you fix lambda, what am I saying? I'm saying that lambda times A plus B equals lambda A plus lambda B for free. If you fix A, I'm saying that lambda plus mu times A equals lambda A plus mu times A. For free also, but for a different reason. Right? In one case, we're talking about linearity inside the algebra, and in the other case, in linearity with the scalars. Okay? But they're both true. It's also true that if you kind of scale by scalars, it's also linear. This is a bilinear map. You just check it, and everything is trivial. Okay? So I have a bilinear map, and therefore I have my map F twiddle. Okay? So instead of saying I need, let me say I use. Because we just checked through some hand waving that this really is bilinear, invoking universality. Okay, so I have a map. Mm-hmm.
Just did you say F bar? I missed something. Sorry, because earlier did you just mention about F bar for this one for K?
So the question is where did F bar go? And actually, I think maybe it's useful if I do a little bit of translation. So when I write F, I say F. If I write this, it's F bar. This took me a long time to understand, so I'm going to write it down. This is F tilde. And this is very confusing to any Spanish speaker because tilde means something very different in Spanish. Or sometimes people say F twiddle, and I don't even know if twiddle is a word. Is it a word? And is this how you spell it? Twiddle? Okay. Oh yeah, like twiddling the thumbs. I know that word. Okay, so and I guess that's probably where the word tilde comes from. Then I don't know. In any case. Samantha's question is where did F bar go in this argument?
No, like did you just have instead of F turtle, did you just have F bar instead like just a few minutes ago?
So the thing is that the reason that you're asking me this is that in my proof of this, I had an F bar. But if you notice, actually in the statement, F bar never appears and I don't need F bar. Okay, F bar was something that I used for the proof. But to actually use this theorem, to use universality, generally you just go from F straight to F twiddle, and you skip F bar. Okay, so I have this, and now I need to check that this is an isomorphism. Okay? So how do you check that something is an isomorphism? Well, there's a couple of ways. You could prove that it's injective and surjective, or you could give me an inverse. You could construct the inverse map. And in this case, I claim that the inverse map is easy to construct. I want to construct a map from A to K tensor A. Okay, that should be the inverse. Now let's see what the natural thing would be. So here, an element of the algebra is just A, and I need to send it to here. So if you're going to send this to something, what would you send it to? One tensor A seems like the most natural thing to do, because one is somehow... I mean, the only distinguished elements here are 0 and 1. And you don't want to put 0 because you would be sending everything to 0. That doesn't have much of a chance of being a bijection. So you try 1. Which one? 1 of the field. You have to check that this is a K-algebra homomorphism, right? So you check that this is a linear map, but this is linear. You check that it multiplies, but if you send AB, you send it to 1 tensor A times 1 tensor B, and we talked about how 1 tensor A times 1 tensor B is 1 tensor AB. So this really is a homomorphism of K algebras. I guess the question is this really the inverse? Because they look a little bit different. So is this the inverse? So the thing is that if you had lambda A here, let's make it look like this. If you had lambda A here, that's going to 1 tensor lambda A, which doesn't look like it's this. But we can move the lambda to the other place, right? Because lambda is a constant, so I can move it to the other side, and now it looks like this, except here, which is where I want it to be. And so that's the inverse. Okay. So of course, when you write a proof, you would say more things than what I wrote here. You would write down what we just said. But that shows that this is an isomorphism because it has an inverse.
So from now on, though, since we've already proven the universality property, you don't have to check for the kernel being 0 or the kernel anymore, right? The kernel of the ideal being 0.
Well, so the question is, did I really have to check that the kernel of this thing is 0? And the answer is yes, because universality produces a homomorphism, but you don't know if it's an isomorphism. A homomorphism gives you have the first isomorphism theorem, which says that the image is this mod the kernel, but you still have to identify what the image is and what the kernel is. And I think maybe that'll be a little bit clearer with my second example. But yes, you still have to check that this thing really is an isomorphism, because this just only produces a homomorphism. Let's do another example, a little bit more interesting. I'm going to tensor two R algebras, two real algebras. One of them is the complex numbers. Is that a real algebra? Well, you need to check that it's an R vector space and a ring. Are the complex numbers a vector space over R? Yes. What's a basis? 1 and I. And you can multiply these guys into, so you can make a ring out of this. Okay. And now this is also an R algebra. Okay, we talked about this one. And so because these are R algebras, I can tensor them. Okay. And what I would like to do is see if I can figure out an easier way of describing this. What would be your guess? Yeah? C of x. How optimistic do you think this guess is? So let's put a little question mark here. We don't know if this is true. But at least it's a natural guess. If you have to guess something, maybe that's the natural thing to guess. And the idea could be that you're kind of taking coefficients from here and sending them to here. Now, there's one thing to be careful about, which is that this is a real tensor, meaning that we can send constants, but we can only send real constants. We cannot send a complex number from here to here. Okay? So maybe I'm trying to maybe worry you a little bit and make you think that this is not obvious, but we're going to prove it's true. I think it's not obvious because you cannot take complex numbers and switch them over like this, but still this is true. So we're going to prove it.
It seems like what we're ending up with is that if we tensor a boring old field with something we don't generally really add a whole lot of structure. I mean, the first example, we're finding that tensoring with K doesn't really change things. Number two, we're finding that we're really not making the situation much more complicated.
Right, so the comment is that when you tensor with a field, it's not that interesting. You're not doing something that exciting. And I'll even say a little bit more about this. That's my example 4. So we'll get there. To say what you're saying in a little bit more, of a more precise way. Or at least a different way. I don't know if a more precise way, but I'll say something to that effect. Proof. We have an isomorphism. Let's build we want an isomorphism, so let's build a homomorphism. Okay. So now I even know what I'm supposed to say. Since this map is bilinear, right? You can already sound slicker. You can already say, okay, since this map is bilinear, then I can make it descend. What map should I use? We take something in here, right? So this is maybe we'll call it Z to make it sound like a complex number, comma, here, a polynomial of real coefficients, what should I send it to? Multiply them. Seems like a pretty natural thing. Is this bilinear? It's just multiplication. We've said it. This is the third time we say it, right? It's multiplication, so it's bilinear. It's bilinear. It descends to the map that we want, at least to some map. Now we want to check that this map is an isomorphism. And well, you could try to build the inverse. It's not entirely obvious how to do that. You can make it work. But just to see it a little bit differently, let's go the other way of checking injectivity and surjectivity. Okay. So let's check injectivity. Why is this? Or let's check surjectivity. That's easier. So I need to make sure that everything here gets mapped to. Okay. Now, to check that everything here gets mapped to, actually, I just need to make sure that a basis here gets mapped to. So what is a basis here? A basis of C of x. X to the m, like 1, x squared, etc. Is that a basis? We're talking about basis as real vector spaces, and therefore so basically we need x to the n and ix to the n, where n you know what I is, where n is a natural number. Okay? And 0 I consider a natural number. Okay? It's important. So f bar of whom is x to the n, and f bar of whom is ix to the n. Example, f of this and f bar of this. Okay. And so this basis is here, and therefore by linearity, this is a surjective map. Okay. Okay, that's fine.
So you're saying it maps basis elements to basis elements, or are you saying that it just has it just gets mapped to by some element in the
So all I'm claiming is that all my basis elements are in the image of this map. And if my image contains all the basis elements, and the image is supposed to be a linear space, and therefore it has to contain everything. Okay. Injectivity. How do we do this? There's several ways to proceed, okay? And in particular, there's shorter ways to proceed than what I'm going to do. But I still want to do this one so that you can see one kind of thing that you can try to do. Suppose that I take something here that maps to 0. Okay? So f bar of now what does an element here look like? It's a combination of pure tensors. Right? So let's say that it's a sum over k of zk tensor pk to the x. And assume that this is 0. Okay? Now, let me write each complex number zk as xk plus, actually let me not use x because I'm already using x for something else, so I'll call it ak plus ibk. And then what I have here is that f bar of ak plus ibk tensor pk of x is equal to 0. Okay? And one reason that I want to do this is so we get used to practicing with computing with tensors. So what can I do now? I can distribute what exactly? So you're telling me to distribute right here. And the reason I can do that is that tensors are distributive. So I can take this and write f bar of f twiddle, sorry. Do I need to do that? I can do that. But can I already, do I already know what this is? We already know what f twiddle does, right? It just takes this times this. And even though I can distribute there, it looks like actually I'm just kind of doing things I don't need to do. Because I know what this is. This is just going to do, I mean, I know f twiddle is linear, and so I just need to apply it to everything, to each one of these things. Okay? And so what this is going to do is that it's going to take this times this. Right? That's what I get. And here I'm using the fact that f twiddle is a linear map. We agree? Okay. So now what should I do here? Well, let's remember who's real and who's not. So everybody's real except for this guy right here. And so we can actually split this into real and imaginary part. Okay. So we can split it into the real part is this, and the imaginary part is this. Okay. And that means that both the real and the imaginary part have to be 0, right? So therefore, this is going to be equal to 0, and this is going to be equal to 0. Okay. Now let's think again. What am I trying to do here? I'm trying to show this thing is injective. I assume that f twiddle of somebody was 0. I need to show that this guy is 0. So can I conclude that this guy is 0? Hopefully. So let's try to do the computation. Okay. But let me circle this guy because we're trying to prove that this guy is 0. So let's compute it and prove that it is 0. Okay. So what is the sum over k of zk tensor pk of x. Well, let me again do what I did here. This is ak plus ivk tensor pk of x. And now I'm going to take the suggestion that I did not take earlier to distribute in the tensor. So I distribute in the tensor, and I get ak tensor this plus I times bk tensor this. Okay. I need to show this is 0. And again, this is a real and an imaginary part, so maybe I can just deal with both parts. With either part separately. So, what is this? Let's deal with the real part. What is the real part is this stuff. Sum over k of ak tensor this. And we need to show this is 0. Can you see why this is 0? It's like we almost have it, except that there's this tensor sign getting in the way. So what should I do? Yep. So with great care, I can take this ak and send it over here. Why do I have to be careful? Well, I just need to make sure that I can move this guy. Can I move it over? I can, because it's real. AK is real, so I can pull it out of here and send it over here. And I get this. And now we're even closer. And now actually what I can do is what can I do? I'll take somebody else. Can I move the summation into here? It looks like it's what I want to do, right? 1 tensor, the summation. So why is that allowed? Because because the tensors are bilinear. So if the first part is fixed, I can play with the second part linearly. And that's great, because now this is 0. So this is equal to 1 tensor 0, which is 0. Finally, okay? So, and the same thing with the imaginary part, of course. So if you want the imaginary part, all you do is take out the a's and put in b's. And the same argument works. And that ends our proof. Yep.
So in summary, this term that you circled over there in purple it's not necessarily true that is 0, right? I mean, we had to prove it first.
So right. So the question or the comment. I mean, I think is not a question. You're saying we didn't know ahead of time that this was 0, and we needed to prove it, and that's exactly what we did in this argument.
But is it necessarily true that for any A tensor B, that if they're both non-zero, that they will give something that's non-zero?
So your question is, if you have A tensor B and A and B are non-zero, does that imply that the tensor is non-zero? Is that your question? Let me throw the question back at you, and I'm going to make you answer it at the end of the class. Or anybody can answer at the end of the class. We'll see the answer to that. Yeah.
So this is sort of 100% actually on topic, but there's some words in the homework that aren't really defined yet.
Yes.
It would be nice
Yes, absolutely. So, okay, so the question is, how am I supposed to do the homework if I don't know the definitions? And the answer is that I will say something at the end of class, but in particular, one of the questions one of the parts I'm dropping. So there's a bi-algebra, and bi-algebra I'm not going to get to define for this homework. So that one you can scratch off the homework. The other stuff, no, let me say that I basically wanted to see where I get today, and if I feel that it's appropriate, then I'm going to give you an extra couple of days to do the homework. That's the plan. Okay. Let's do another example. Do I have a natural map from V tensor W to V? So, I don't know, nice, natural, whatever you want to put here, some adjective. Nice, natural. Let's try to answer that question. So, well, what is the most natural map that this could be? We have a map called the projection map from V times W to V. So the first try, you could say, well, since this map is bilinear, then the answer is yes. And the map being this. Okay. That looks bilinear enough. Does it?
Wait, let's actually check.
Well, maybe, if you always have to check. This seems like it could be bilinear, but let's see if it's bilinear. Okay, so for example, if you fix W, is this linear in V? Yeah, because it's just the identity map. If you fix V, is this linear in W? This is actually not linear in W. Right? Because, for example, what is f of you need this, right? You need V comma W plus W should be equal to V comma W plus V comma W. Or you need this for any. But this is V, and this is V, and this is V. And that's not true. Okay. That's not true unless V is 0. Okay. Well, and that's why I said first try, because this try is a failed try. Okay. So this is not bilinear. This is not bilinear. And therefore, this first failure. But you always learn from your failures, and it's good to see something like this. Okay, this is how you show. This is how not to construct a bilinear. How not to construct a map from a tensor product to somewhere else. Okay, so let's try something different. Let's try to define a function. Can I put something in front here to make this linear? So for example, I mean, the first thing you might try is to put W, but the problem is that you can WV doesn't make any sense. So two vector spaces, and we're looking for something in V. Notice that if we're looking for something that lives in V, I mean the image should be in V, and this is a vector in V. So actually, what you need to put here is pretty much a scalar. So what scalar do we put here?
Can we put a W, map W to the underlying field for V, because both of them are some very space, right? And they share the same underlying field. So we send W to that field, can we?
So right. So the question is how to. So let me rephrase what you said. We need to send W to an element of the field. So how do you send something in a vector space to something in your base field? There's actually many ways to do that. Because you just to send a vector to a number, you just take a linear map. That's the most natural thing. So you could just put here G of W, where G is any linear map. Okay. This is going to be for fixed W, the red stuff is constant and is linear in V. And for fixed V, the V is constant and G is linear by definition. So this is a bilinear map.
So we need this to be. We need this to depend on. It can't be constant. It needs to be different for each value.
Well, it could be constant, but how many linear functions are constant? The only linear function that is constant is 0. And that could work, and that is a very silly bilinear map to send everything to 0, but it is a bilinear map. Anyway, so this works. This works. Now, what is maybe the simplest linear function that you can think of? Let's say we have a basis. So the point is that there's many choices. Any function G will do. So notice any G. Let me introduce a notation that you've seen, that maybe most of you have seen. W star is the space of linear functions. W to the field. Any G will do. And for example, one easy way is that if you have a basis for W, you could just let G be projection into one of the coordinates. That's maybe. So for example, if Wi is a basis for W, then an easy choice would be you could use Gi to be projection onto the ith coordinate. Okay. You just look at the ith entry of the vector with respect to that basis. That is an example of a map from V tensor W to V. Okay. And so maybe the answer to this is that, I don't know, do you think this is nice? Maybe it's not as natural, it's clearly not as natural and canonical as it is, as projection is, to go from V times W to V. So it's not canonical, it's not as natural as before, but they have a lot of flexibility. There's actually many. So maybe you don't think it's as nice, but at least you agree that there's numerous options and you get to pick. Okay? Yeah.
When you did the first example of the projection onto V, you said it turned out not to be bilinear. Isn't what you're doing at the bottom? Isn't your G example of projecting an ith coordinate?
So let's revisit what I did earlier. What I did earlier was just define this to be V. In other words, I wanted to define G of W to be 1. So is that a linear function? No, because the function 1 is not linear. The function that sends everybody to 1 is not linear. And so that's why this doesn't You should check it. Projection is linear. Okay. So this is actually very useful, and I'll show you an example of this, which will answer several of the questions that you've asked me. So here's a useful lemma. A useful lemma. Let's say that you have a basis for W, then and let's suppose that you have something like this. Let's say that you have a sum of pure tensors equal to 0. Okay? That doesn't seem too unlikely to have some tensors that add up to 0. Let's say, I don't know what's.
The vector space which are finite.
I hate putting subscripts on subscripts, but I guess I'll do that. Okay. So W sub J sub I. I don't like doing this, but I'm going to do it fine. V sub I, sure. So basically, a sum of tensors equal to 0 where the right-hand side is part of a basis. Then what is true? This might surprise you, but actually every single Vi has to be 0. So what's the answer to your question, Nino? So remember, Nino's question was if you have A and B, or let's call them V and W, V in capital V, W in capital W. If V is non-zero and W is non-zero, can you guarantee that V tensor W is non-zero? This says the answer is yes, because W is independent as its own thing. Okay. Proof. How do we do this? Well, yeah.
For this W, J sub I in the tensor, are they simply elements in W, or they are actually things inside the basis? Which one is that?
So this is just taking a subset of the basis.
So these are actually each of these.
If you're thrown off by this double subscript, just don't worry about it. All I'm doing here is taking a finite subset of this. Okay. That's right. I mean, it is. I agree that.
Isn't everything finite?
Huh? No, no. W could be infinite or uncountably infinite dimensional, whatever. Yeah. And that's why we have to do this trick. So you're basically picking a subset of these guys and taking a finite sum like this. I'm going to show that proves that Vi has to be 0 for all I. And the way I'm going to do it is that I'm going to consider the function G sub the function that just projects to this coordinate. Okay. So So this is just the projection onto the jth coordinate, and let's say that you kind of, I'm going to define it like this, okay? So if j is ji, I make it 1, and otherwise I make it 0. Let me not assume any inner products, anything like this. I'm just kind of taking a dual basis. If you're used to this kind of thing, we'll say more about it. I'm just defining a linear function that sends the particular basis vector wji to 1, and all the other ones to 0. Okay, that's what I mean by projection here. Just look at that ji coordinate, okay, and apply my function that I get here, f as in example 3. Okay, so I apply f to this. F of the sum from I equals 1 to n of vi tensor wji. Okay, so what is this? Well, f is linear, so I get this. Okay, and what is this? Well, I mean, let's actually just write it all out. So f of vi tensor w ji, what I do is that I get my too many subscripts. I'm just going to write g here. Okay, g. So g of wji f of vi. Now, what is g of wji? It's usually 0. The only time it's not 0 is for this guy. So in other words, for ji, and so what I'm going to get here is, this is just a bunch of zeros except 1, 1, which gives me f of vi.
The sum of VBI should be sum
I think this is right. Everything died except for f of v.
I is a running index in one case, and you end up with an I on the outside.
No. So here, and you guys are sticklers. That's good. It's a good thing. Let me call this k, I. It's good. I'm glad you're checking the details. It's very important. So here, everything died except for vk. I'm fixing k. Okay, and sending variable jk to 1, all the other ones to 0. And then when all of this is said and done, all I get with this computation is f of vk. But what is this? This is f of 0. And what is f of 0? Well, f is a linear function, so f of 0 has to be 0. And that shows that this f doesn't need to be here. Sorry. F of vi tensor something is, you put the v, and then you apply the function to w. So the vi gets here, you apply g to this guy, and so all you get is vk. And so what I showed is that for each value of k, vk is equal to 0, which is what I wanted. Okay. And so this is how you can begin to see the kinds of things you can do. If you want to show that something is 0, just kind of map it places and use linear functions the way that you're used to, and that'll work. Okay. Now let me